what we're going to do next is we're going to use formal charge to sort of suggest a best structure for a compound. And it turns out you can often draw Lewis structures of compounds more than one way. And one of the things that we use to try to determine which structure is correct is the formal charge of the structure. So, give you an example. This is hypochlorous acid, or it could also be drawn like this. And it turns out for many, many years it was drawn as this structure. And if we draw a skeleton from that, what we'll find is that we can go like this. Or we can draw it like this. Now, both of these structures can give us somewhat valid structures for hypochlorous acid. So let's go ahead and calculate the number of valence electrons, and then we'll distribute it on the structures, and we'll do formal charge to see what the formal charges of the structures are. So I have hydrogen, which is 1. So this is my valence electrons, right? And then, actually, I'm going to draw it at the bottom because I could just use some extra space. It's going to be 1 times 1 for the hydrogen. It's going to be 1 times 7 for the chlorine. And 1 times 6 for the oxygen. So that gives me a total valence electrons of 14. Now, I could subtract off my skeletal electrons. And that's going to be 2 times 2. So the remaining electrons to distribute is going to be 14 minus 4. So I have 10 left to put around the structure. Now we'll start with the oxygen. There's 6 of the 10, and I have to have 4 more, like this. Now if I started with the chlorine, I'd end up with the same kind of arrangement. But let's do the oxygen here first. I got my 8, so I have 6 more. And there you go. You have two Lewis structures. As far as octets go, they seem to be equivalent. Okay. Now what we're going to do is we're going to calculate formal charge. So for oxygen, again, going back to this diagram, right? Oxygen should have 2 bonds and 2 lone pairs. Now, it doesn't. It has 1 bond and 3 lone pairs. So it actually has more electrons that it holds than oxygen with 2 bonds. And so you would predict this has a negative charge. So let's go ahead and calculate it. It has 6 valence electrons minus 1 bond minus 6. So that's a minus 1. So I have a minus 1 charge on this oxygen. The chlorine has 7 valence electrons, but it has 2 bonds. And it has 4 lone pair electrons, so that's plus 1 charge. So in this structure of hypochlorous acid, right, I have a positive and a negative on the adjacent atoms. Now, if I do this structure, remember, oxygen with 2 bonds and 2 lone pairs, you'd expect the formal charge to be 0, so we're just going to write that in there. Now, chlorine has 1 bond and 3 lone pairs. Now, chlorine is in the same family as fluorine. So fluorine and chlorine both, and bromine and iodine, if they have 3 lone pairs and a bond, they should have a 0 formal charge, and so this has a 0 formal charge. Now, what Coulomb's law tells us is this is a relatively unstable situation. What really wants to happen is those charges want to be canceled out. And if we draw the structure with the hydrogen on the oxygen instead of on the chlorine, right, you notice that you have a 0 formal charge. So it turns out the best structure is this one. And experimentally, that bears out that the hypochlorous acid, the hydrogen, in fact, all the polyatomic oxo acids, that is anything with a polyatomic ion containing oxygen, right? The acidic hydrogens are always on the oxygens. So the more stable structure is the one we judge to be the better structure. And it's the better structure because we minimize having opposite charges on adjacent atoms. So let's see how formal charge can be used to determine the best structure for sulfate or sulfite ion. So we're going to draw a sulfite ion. And we'll make note about its resonance structure. That's not the main point of this, but we'll also note how many resonance structures it has. But SO3, I'll put sulfur in the middle. Oxygen's around. Count the total number of electrons. So sulfur and oxygen both contain 6 valence electrons. So that's 24. Electrons plus 2 electrons for charge. So a total of 26 electrons. Now, what I'm going to do next is subtract off again the skeletal electrons. I'm just going to write that note there. It's 6. So the remaining electrons to distribute will be 26 minus 6, or 20. So then I'll go ahead and distribute 1, 2, 3, 4, 5. Oh yeah, right? You tired of that yet? Let's do this. I'm going to distribute them as pairs. This is like everybody's favorite thing, okay? 20 divided by 2, right? So I'm going to distribute pairs of electrons. That gives me 10 pairs. Now, when Lewis and a guy named Speakman actually were two early voices in the Lewis structure idea, originally drew structures, they often drew the pairs of electrons like this because they weren't sure, or they were trying to see where else it could bond, right? So lone pairs were actually drawn as lines. I've taken liberty at that and decided I'm going to do this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you don't actually have to draw dots. If anybody argues with you, you can say, well, Lewis did it, and then you can sort of move on from there. And if you need to see pictures, if you're ever interested in like historical, like science stuff, I have books from both of them. Anyways, is that structure done, right? Well, everybody has an octet, but we haven't calculated formal charge. And so what we need to do is we need to look at the formal charges of each atom. And so oxygen, for sure, we need to check its formal charge, because remember, oxygen, 2 lone pairs, 2 bonds. It definitely is in a situation where it's not that. And if you remember, it's -1. That is a completely legitimate way to do these structures. I'll want to see a calculation, for example, if you're doing a quiz or scratch paper or something like that, or worksheets, things like that. But -1, so let's see how we get that, right? So it's going to be 6 valence electrons minus 1 bond, minus 6 lone pair electrons. That's where I get the -1 from. Now they're all the same, so I have minus, minus, and minus, okay? And then I have to do the sulfur. So if I'm going to do the sulfur, what I need to do is I need to, again, do the same calculation like I did for oxygen. But what do you think it might be, right? Remember the formal charge, if you add all the formal charges up, they need to equal the overall charge. Right now I have a -3 charge. But the overall charge for sulfite ion is -2. Which means the sulfur has a +1 charge in order to make this work. Because if you made this positive, right, then you'd have a total. These 2 would cancel, or a positive would cancel one of the negatives, and then you'd have 2 negatives left over, and that would be the sulfite overall charge. Now, what we're going to do, though, is this. We'll go ahead and do the calculation just to see it, right? It has 6, and then it has 3 bonds. I'm subtracting the 3 bonds, and then I'm subtracting 2 electrons for the lone pair, and I get +1. Okay? So its formal charge is +1. Now, this is what we're going to do. When you see a structure like this kind of default action, you're going to create a double bond. Now, it doesn't matter which oxygen you make the double bond with. But notice what that does. This is still -1. This is still -1. This one's 0. This implies that the sulfur's formal charge is 0. What's the problem, though, right? The problem is that it has 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And it violates the octet rule. So the deal with the octet rule is, and it's been mentioned before, but the deal with the octet rule is it's for the s and the p orbitals. So sulfur is in the third period. And because it's in the third period, that's when we introduce in quantum mechanics the idea that it has a 3d orbital. And so what sulfur does in order to make this extra bond is that accesses energetically favorable d orbitals. That's what the phrasing is. That's the phrase I'll mention later as well. But it uses d orbitals that are available and within the energy range of the molecule to create the bonds. Okay. So since it's in the third period, the 3d orbitals are available, and so it uses those to expand its octet. So this does violate the octet rule, but what it does is it also allows us to eliminate formal charge. So what we're going to normally do in these situations, is eliminate the formal charge in favor of expand I don't know how to say it, in spite of expanding the octet. Okay, so we're going to eliminate formal charge in spite of expanding the octet. So this will have a formal charge of 0, and we can do the calculation just so you can see this, because it's the first one of these that we've done, right? It's sulfur, right, is going to be 6. Now it has 4 bonds, and it has 2 lone pair electrons. So that's where we get the 0 in our calculation from. So even though it doesn't look like what you'd expect to have a 0 formal charge, there are multiple ways for atoms to have 0 formal charge. Anytime it looks out of the ordinary, you need to calculate it. Well, because it has a double bond, right, it now has possibility of resonance structures, because the electrons that formed that double bond and killed the formal charge could also have come from this oxygen or this oxygen. This is an ion, so we do have to put brackets around it. All right, and then the resonance structures would look something like this. And again, use lines, it's much faster. The resonance arrows is what we use. Oops. Like that. Okay, and if you were doing the bond order, right? It doesn't ask for that, but if you're doing the bond order, there's 3 structures, right? And then there's 1, and just pick one of the bonds. There's a bond order of 1, 2, and 1. So 1 plus 2 plus 1. So it ends up being 1 and 1/3 as the bond order. Okay, so here's one for you to practice with. It's sulfuric acid. So the sulfur goes in the middle. Just a couple of tips here. Sulfur central. And then the hydrogens are on oxygens. And you can come up with a bunch of different structures this way, but the sulfur is in the middle, right? And then the hydrogens are attached to the oxygens. So go ahead and draw the Lewis structure, look at the formal charges, redraw it, and try to see if there are any other resonance structures. All right, so here's the structure. I didn't include the calculations of the valence electrons and everything, but here's what you see. You have, when you draw your structure initially and just satisfy the octets and calculate formal charges, these are the formal charges that you get. You notice I only calculated the ones in the middle here because I knew this would be 0 and this would be 0. And hydrogen only takes one bond, so this one will also be 0. So when I calculate it, though, I get a -1, a -1, and a 2+. So what I can do is share a pair of electrons, literally just take and move a pair of from being a lone pair to being a bond on both sides. Okay? When I do that, I end up with a double bond and then 2 lone pairs, double bond, 2 lone pairs. So that's 0, that's 0. Since the rest of it's 0, the sulfur has to also be 0, but we'll check that with the calculation because it doesn't look like you'd expect, right? Oops. Formal charge for sulfur would be 6 minus, and how many bonds does it have? It says 1, 2, 3, 4, 5, 6, so 6. And there are no lone pairs on the sulfur, so that's a total of 0 for its formal charge. So that works out. That is the best structure, the one that we normally expect to see for sulfate ion.